Okay, so last time we met, we were talking about converging nozzles, and we were talking about how a converging nozzle is always subsonic. You might reach Mach 1 at the throat under certain conditions, but you'll never reach supersonic flow in a converging nozzle. Now, we also talked about a converging-diverging nozzle in which it goes from subsonic to supersonic, and it leaves the exit at supersonic conditions. That's called the supersonic design converging-diverging nozzle. So we look at the road map, and I'm going to put the road map here. This is P over P naught, and this is the throat. This is the exit. This is 0. And this is P over P naught of 1. This is 0.528 if K is 1.4. Okay, so this is called the back pressure region. This is the exit pressure here. This is the shock wave here. It's probably best to call these guys 1 and 2. 1 is the upstream values in front of the shock wave, 2 the downstream values in back of the shock wave. T stands for throat. P naught, T naught, reservoir pressures and temperature. Okay, so let's go through the specific conditions here for this example problem. P naught is 300 kPa. T naught is 500 K. The area of the throat is 1 square meter. The area where the shock is 2 square meters. And the area of the exit is 3 square meters. We're going to call the exit area 3. So the shock is assumed to be very, very thin, so A1 and A2 are the same thing. They're both 2 square meters. And the exit area is A3, that's 3 square meters. And the fluid is air. And we're asked to find, various things. I'm not going to write them all down, there's just too many. But we're asked to find many, many things. All right, so the first thing is to decide where we are on the road map. Okay, here's the road map. No flow. If the back pressure is equal to the reservoir pressure, nothing causes flow. So if the back pressure equal the reservoir pressure, no flow. As we reduce the back pressure, we start to get flow. And it looks like this. I'll draw a couple curves here. If we keep reducing the back pressure, we eventually are going to reach a Mach number at the throat equal 1. At the magic number 0.528 for K of 1.4. Since the back pressure is still up here somewhere, it kicks back and it goes back to subsonic. Or if the back pressure is way down here, it can go on down here where it's supersonic. Subsonic here, supersonic here. Now, if there's a shock wave somewhere, then it looks like this. So, there's our picture. we know what line we're on the road map. I'm going to erase these to show you where we're at. We're not up here. There's a shock wave. We're not 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 here. There's a shock wave. There we are. That's where we are. A shock wave is in the diverging portion of the nozzle. Okay. Now we do our road map here. From here to here. The Mach number is 1 at the throat. Up here, the Mach number is less than 1, subsonic. From here to just in front of the shock wave. Just in front of the shock wave, supersonic. Downstream side of the shock wave. We know across the shock wave, the flow goes from supersonic to subsonic. And outside here, of course, it's still subsonic. So there's our flow regimes. Now comes, where do you go to find numbers? Subsonic isentropic, table B1. Supersonic isentropic, table B1. Across the shock, table B2. Subsonic isentropic, table B1. So there's where you go to find the answers you need. What table do you go to? B1 subsonic, B1 subsonic, supersonic, across the shock, B2, back to subsonic, isentropic, table B1. All right, so let's then find out, that we know that the Mach number of the throat's 1. Okay, why do I know that? There's a shock wave. Anytime there's a shock wave in the diverging portion of the nozzle, there's going to be Mach 1 at the throat. Okay. At location 1. All right, so 1 at location 1 there. Upstream of the shock. A1 over A1 star. A1 is 2 square meters. A1 star is 1 square meter. What does the starred condition mean? It means where the Mach number reaches 1. So at the throat is where the Mach number has reached 1. So A throat is the same as A star 1. Why is it A star 1? Don't forget, in any subsonic region, A star does not change. In any region, isentropic, A star does not change. A star is the same from my left hand to my right hand. A star is the same. Okay, so A star 1 is 2. I go to table B1. And I have the Mach number in there. Here we are. And not 1, just the Mach number. P over P naught. Rho over rho naught. T over T naught. A over A star. Okay, go down here. Mach number there. A over A star is 1. And let's see, okay. I'm trying to find A over A star of 2. So here it is, 2. Whoops, there's one down here too. In that table, B1, the isentropic tables, there are two places where you're going to find A over A star equal 2. But here's the key. This one up here is subsonic flow. This one down here, supersonic flow. What do I have at point 1? Here's point 1. What do I have? Supersonic flow at point 1. So, which one do I want? I want the supersonic Mach number. That guy is 2.20. Okay, now I've got Mach 1. So, table B1, Mach number at 1 equal 2.20. Got it. I also have P over P naught, 0.0935, P over P naught. So P1 over P naught 1, 0.0935. Solve for P1. So P1 comes out to be 28.06 kPa. So now I've got the pressure in front of the shock wave. Now I go to the shock tables from table B2. Across the shock, okay, table B2. Okay, table B2, we've got Mach number 1. We've got Mach number 2. We've got P2 over P1. That's static pressure. We've got rho 2 over rho 1, which happens to be, it can be shown it's the same thing as V1 over V2. You can prove that. And then we have T2 over T1. And then we have P naught 2 over P naught 1. We're not done yet. And then we have A star 2 over A star 1. Okay, I know Mach number 1, 2.2. I go to the table, Mach number 1, 2.2. Downstream Mach number, subsonic, 5.471. So it went from supersonic to subsonic. 5.471. Okay. Let's see what's next. That's the Mach number there. Okay. We can get P2. P2 over P1. .48. The pressure really goes up across the shock. 5.48. So P2, I know P1. I just found P1. So P2 comes out to be 154 kPa. Okay, I'm going to get P naught 2 over P naught 1. 0.628. Okay. This is all from table B2, pardon me, table B2. Okay, I know P naught 1 equal P naught, 300. So P naught 2 is equal to 188 kPa. Okay, so I've got that. Okay, now, next. P2 over P naught 2. I know P2, it's right over here. 154 over 188. Uh-huh.
What does P naught 2 represent?
When you go across the shock, it takes energy. The stagnation pressure is a measure of how much energy the fluid has. To fight the shock, to push the molecules through the shock wave takes energy. So this energy goes down. What was P naught 1? 300. It went down to 188 because it took a lot of energy to push that molecule through the shock wave. So the energy the fluid has is P naught is a measure of the energy the fluid has. So this guy's ratio is 0.819. I go to table B1. P2 is going to be what now? Be careful. See, P2 is subsonic. It says go to table B1. Okay, go to table B1. Look for a pressure ratio of what? 819. So 819 is going to be subsonic. There's a pressure ratio. A over A star. 1.255. Table B1 at P2 over P naught 2 equal 0.819. I get A2 over A2 star equal 1.255. So I get A2 star equal 1.592 square meters. A star changes over a shock wave. In isentropic region, A star remains constant. A star changes over a shock wave. What does that mean? That means once you cross the shock wave, that is now subsonic. Now it's subsonic. If you want to reach Mach 1, what do you have to do? You have to go down to an area here, which is 1.592 square meters to reach Mach number equal 1. From where you were here, what's the Mach number there? Mach number 2, did I get it? I guess I got it here somewhere. Let's see, no, I got Mach 1, Mach 2, yeah, Mach, no, I didn't get Mach 1. But that's Mach, oh, there's Mach, here's 0.547. Mach number 0.547. To get to Mach number 1, make the area go down to 1.592. That's what it means as far as seeing the change in the A star. 2, 3, exit pressure, back pressure. Okay, back to here. Okay, where were we? Down there, got the A star 2. All right, now notice it again. Does A star change in an isentropic region? No, that's A star 3. Does P naught change in an isentropic region? No. P naught 2, 188. P naught 3, 188. Stay the same. Okay, go over to here. At location 3. A3 over A3 star equal 1.884. Table B1. Why? It's isentropic. Read the road map. Table B1. Is location 3 subsonic or supersonic? Look at the road map. Subsonic. Go here to table B1. Find the A3 over A3 star over here. Okay, that would be over here. From table B1, Mach number at 3 then, 0.330 subsonic. P3, 188 times 0.928. That 0.928 is P3 over P naught 3. Table B1. P3, the pressure at 3 comes out to be 174 kPa. But that's also equal to pressure, back pressure, because P3 and P back are the same thing. There's P3, there's P back. They're the same thing. One more. Find T3. T naught equal T naught 1 equal T naught 2 equal T naught 3. Remember, the stagnation temperature does not change in an isentropic region or across a shock. T naught does not change in an isentropic region or across the shock. Okay, it's the same. So if I want to find T3, I go back here where the Mach number 3 is 0.330, table B1. It's subsonic, it's up here somewhere. I know the Mach number, it's 0.33. I go over here, T3 over T3 naught. And I read 9782. So I solve for T3. The exit temperature, 489 Kelvin. If I want to find the mass flow rate, I can do this. Or I can do this. Or I can do this. Or I can do this. That was our equation in there, and I think that was for the maximum mass flow rate, and I think, did I have that? I think I do. Yeah, it's here. There it is. 0.6847. P naught, A star, divided by the square root RT naught. Do I have P, wait, now that equation, only for choke flow. This equation, choked or not choked, doesn't matter. This guy, only choke flow. Is he easy? Sure. I was given P naught. I was given T naught. I know A star. What A star is that? That's the A star at the throat. That's A star at the throat. 1 square meter? Yeah, 1 square meter. If you do that, you end up with, I think I've got an answer on that. Let's see. 537 kilograms per second. So this is really a complete problem. These guys with shock waves in the diverging portion of the nozzle are really, really, really very complete that way. You go everywhere. You go from table B1 subsonic to table B1 supersonic, back to table B1 subsonic, across the shock, table B2, everything. A star changes across the shock. P naught changes across the shock. T naught doesn't change across the shock. All kinds of rules like that you have to go through to determine where you're going. And sometimes it gets hard to see where you're going. You can do all this by equations, but you can kind of get the idea. It's pretty tough stuff. It really helps to have the roadmap there and here especially, and those tables. That really helps to see where you're going and how you're going to get there. Okay, let's do another one. This is in chapter 9, 957. So let me pull out that problem from our textbook and see what that one looks like. 957. Okay, air flows from a tank through a nozzle, converging, diverging, into a standard atmosphere. The normal shock stands at the exit of the nozzle. Okay, so now a different picture. The problem, 957, said the shock is now at the exit plane. So now the shock is right here. Okay, let's see what we're given. We're given the fluid is air. Okay. I am not given P naught, unknown. I'm given T naught, 270, 373. It's 100 degrees C, so 373 K. Area of the throat, 10 square centimeters. I'm not given that. Yeah, I'm given that. A1 is 12.5 square centimeters. Exit area is the same as out there. Right, got them all. I'm going to call this 1. I'm going to call this 2 across the shock. Okay. Let's see what else. Oh, P back is atmospheric pressure, 101 kPa. Okay, find P naught and M dot. We weren't given the reservoir stagnation pressure, P naught. Okay, back to here again. Our roadmap now goes down here, shock wave at the exit and goes out here. Here's P back. Here's P1. Here's P2. Okay, is it choke flow? Yeah, we went, anytime there's a shock wave, we know we have choke flow. Okay, so we know we have choke flow. Is that the maximum mass flow rate? Yes, that's the maximum mass flow rate. And I'm just going to put this here so we know. Only use that when you have choke flow. Otherwise, you can find the mass flow rate anywhere you want, at the throat, at 1, at 2 by rho AV. Okay, back to here. There's our roadmap. So here we go again now. Let's see. From here out to here, let's just draw that and we'll draw that. From there to there, supersonic table B1. Across the shock wave, table B2. Out here, subsonic. Okay, there's our roadmap. All right, we start out and we say, okay, now I know this is the picture, what's going on. So I'm going to take A1, since I know it, and A through it and take the ratio. So first, A1 over A throat is equal to 12.5 divided by 10. 1.25. Got it. Table B2, shock table. Mach number 1 is equal to 1.60. 1.25. So my area ratio is 1.25. Is that supersonic? Yeah, it's a shock wave. Supersonic, my roadmap shows me. So I go in there with this area ratio, 1.25, pardon me, and I end up with a Mach number of 1.60. So I know the Mach number now is 1.60. I also know that P2 over P1 is equal to 2.820. 2.820. Okay, so, and I know P2 equal P back, and the back pressure is 101 kPa given to me. P2 is the back pressure. Okay, so now I can solve for P1. So P1 is equal to 31.82 kPa. Okay, at the Mach number equal 1.60, that's a Mach number 1. P1 over P naught, 2353, table B1. Why is that? Because when I'm in point 1, I'm in table B1 region. Okay, go to table B1. P1 over P naught, that. Did I find P1? Yeah, I found P1's right there. So solve for P naught. So P naught is equal to P1 divided by 0.2353, and that gives me 135.2. So that's how I find the pressure in the reservoir in order to cause those things to happen, the shock at the exit plane. Part 2, find the mass flow rate. Well, we know, since it's choke flow, you might as well use the easy equation. M dot max is equal to 6847 times A star P naught divided by the square root RT naught, and A star is the throat area, 10 square centimeters. I didn't calculate it, but it's pretty straightforward, obviously. So again, you have to use table B1 and table B2 because there's a shock somewhere in the diverging portion of the nozzle. In this case, the shock is at the exit plane, and the pressure across the shock, P1 on the upstream side, P2 on the downstream side. So 2 examples with a converging, diverging nozzle. One, a shock wave is somewhere in the middle. Next one, the shock wave is at the exit. So we're going to stop here on that, and we'll pick it up then next time.